All right, solutions. This first part is going to be a review from first semester. Remember, there's two types of matter. There are pure substances and mixtures. Within pure substances, you have elements and compounds. And compounds can be separated by chemical change. In other words, I could break down sodium chloride back into sodium and chlorine. Elements like sodium and chlorine cannot be broken down any further and retain their identity. Okay. Mixtures. Remember, there are two types of mixtures. Homogeneous mixtures or homogeneous, your preference in how you say that. And they have a uniform composition, meaning they look the same throughout. Remember, we also call those solutions. Title phrase for the unit is solutions. Excuse me. And then, of course, a heterogeneous mixture does not have uniform composition, so I can visibly distinguish its parts. And two examples of that, subcategories of heterogeneous, is suspensions and colloids. Okay? This all seem familiar? Good. Okay? Within the types of mixtures, let's talk a little bit further about solutions, which are the homogeneous mixture. Any substance, solid, liquid, or gas, that is evenly dispersed throughout another substance. It is not a chemical reaction. When I dissolve sugar in water, it is not a chemical reaction. It is a physical change. Some examples. How many of you wear contact lenses? You use contact solution, saline solution, to put them in your eyeballs. If you've ever been in a hospital or seen someone in a hospital with an IV, the fluid's in there, that would be an example of a solution. It would be a buffered solution, but those are examples of solutions. You're sitting in a solution right now. What are you sitting in that's a solution right now? Air. Very good. Components of a solution. This is something that we didn't really talk about last time, but you do need to know. And that is, you have the solute and the solvent. The solute is what is being dissolved. So like, let's go back to sugar water. Sugar would be the solute. The solvent would be the water, what you're dissolving it in. Okay? Remember from the video, water is a universal solvent, because water has the ability to dissolve polar and ionic compounds. So it's really actually hard to keep good, clean, pure, deionized water because it dissolves so many things. Suspensions, of course, particles are so large that they settle out unless they're constantly stirred or agitated. So there's some examples: muddy water, salad dressing, Italian salad dressing, Lucky Charms would be a heterogeneous mixture. Salad, paint, those are all examples of heterogeneous mixtures of a suspension. Colloids are kind of like in between suspensions and solutions. Colloids have intermediate sized particles that will not settle out, but they are not a solution. They're not always evenly dispersed, and they will exhibit the Tyndall effect, if you remember what that is from last semester. Tyndall effect is I pass a beam of light. If it's a solution, it passes through, you don't see it. But if it's a colloid, it scatters that light. And remember, we used the example of fog. Other examples of colloids are shaving cream, Jell-O, paint. Those are some other examples. The colloid has two phases: the dispersed phase, which is the colloidal sized particles, and then that's a typo in your notes. It should be dispersing medium. Basically, it's kind of like the solvent. They don't really call it a solvent, but that's comparative to a solution. You have the dispersed phase and the dispersing medium. Colloids exhibit something called Brownian motion, which, if I were to look up the colloids under a microscope, it would look like the particles were moving around, kind of like if they were alive, but they're not alive. And so that's Brownian motion. Kind of an example of that is if you've ever been in like a concert or whatever, and they pass the beam of light, like if you're in the auditorium and they're passing the spotlight or this laser, you see the particles in the air floating around. That's kind of like an example of that. It's like a rough example. It's not like a true example, but you get what I mean. Yeah.
Or like when the sun passes through a window.
Right, and you see, like, comes in your house and you see, dang, there's a lot of dust in the air. You can't see it that's an example. That would actually be more of an example of, it's also an example of the Tyndall effect a little bit. Yeah. There's some just fun facts about colloids. You can go back and read those if you want. You've seen that picture before because I used it last in the first unit where we talked about it, just to refresh your memory. Difference between a colloid and a solution, and the most common one that you're familiar with is fog. On a foggy night or day, you do not use your high beams because it scatters the light, because that would be a colloid. Whereas on a clear night, if it's just air passing, it is a solution, and you don't see your headlight beams. The solution process, we call that solvation, and it's the process by which a solute dissolves in the solvent. If something is miscible, that means that they mix and they can form a solution. If something is immiscible, that means they will not form a solution. So like oil and water are immiscible. And then, of course, aqueous solutions means the solvent is water. Okay, example of that would be salt water or saline solution. Okay, moving on through this review process. This is something I usually make them write down, but if I were you, I'd take a picture and make note of it later so we don't have to sit here and wait for y'all all to write. And that is, these are the types of solutions. We tend to think of a solution as a solid being dissolved in a liquid, right? That's what we tend to think of, okay? But there are all kinds of solutions. We said earlier, you're sitting in a solution. That is a gas dissolved in the gas, okay? You can have a liquid in a gas. You can have liquid and liquid, solid and liquid, liquid and solid, and solid and solid. The one that they truly do forget about is a solution of a solid in a solid. And those are examples of our metal alloys that we talked about, like brass and bronze, stainless steel. Those are solutions, okay? We could separate those out by hitting the melting points of the different metals and pull those metals back out of that solution. But we tend to not think of solutions as solids. We tend to think of them as liquids or gases. So that's in there just to remind you of that alone. So this part is not in your notes. It's there for me to kind of explain to you what's happening when you are dissolving something. And it depends on whether you're doing ionic or whether you're doing polar or nonpolar. So basically what happens when you are dissolving an ionic compound in a liquid, and we're going to go with water, okay, because that's what we care about. That's what most of our reactions are going to be in our, not reactions, calculations. So basically it takes energy to do, there's two processes that take energy and one process that releases energy. First of all, when I dissolve the solid has to break apart and to ionize or dissociate. So that requires energy. I have to put energy into the system to break apart. Let's just go with sodium and chlorine. To break them apart and say I got sodium ions now and I got chlorine ions. And then energy is also required to separate the water molecules, because remember they're held together by hydrogen bonds. So I got to separate the water molecules from each other to make room for the ions to go into solution. And so that also takes energy. And then the third process is the water molecules now will surround the positive and negative ions. That process usually releases energy when they do that. Okay? And so now this solid that's been dissolved is said to be hydrated. So that means it's surrounded by molecules of water. If you had to make an educated guess, water is polar, right? It's got a slightly positive and a slightly negative. So if I'm talking about sodium chlorine, what part of water is going to surround the sodium ion? What's going to face it? The positive or negative end of water will surround the sodium. The negative, right, because opposites attract, right? So around the sodium, the water is going to be oriented where it's got the negative or the oxygen end up to it. And then the chlorine ion is negative, so what part of water would face it? The hydrogen, right, wherever the positive end, okay, because they're going to be opposite. So there is a picture of that. So if you see the green are the sodium and the gray are the I said that exactly backwards. The green are the chlorine and the gray are the sodium. So if you look at the green, it's the positive end of water that's pointed to it. And if you look at the gray sodium, it's the negative end of water because opposites attract. So that's how it surrounds it and hydrates it, is the positive end of water is attracted to the negative chlorine. The negative end of water is attracted to the sodium. So that's how it's able to dissolve ionic compounds. Okay? What if I have polar covalent? Let's go with sugar, table sugar. Okay? Polar covalent will dissolve, obviously, but in covalent compounds, dissociation or ionization does not occur. In other words, the sugar doesn't break up. It stays as one huge molecule in the water. But because it's a polar molecule, it has a positive and a negative end. So then water, kind of in that picture, shows water surrounds. Again, the positive side of water is going to be attracted to the negative pole in the glucose. Okay? But we don't call that hydration. We call that molecular solvation. And then last, if it's a nonpolar and water, a solution will not occur because there's nothing for water to be attracted to on that nonpolar molecule because it has no positive negatives, so there's nothing to be attracted to. So that's where you get layers. And so oil and water, obviously we know this by now, don't mix. Oil has less density, so that's why the oil floats on the top. Okay? So that brings us to solubility, how we can figure out how much of something will dissolve. So anything that has will dissolve, we call it has a solubility. And the solubility graphs that we're going to look at, if you look at the y-axis, it's going to always be 100 grams. How much will dissolve in 100 grams of solvent? And usually we're going to be talking about water. So there are three types of solution when we're talking about we've made a solution, and they are unsaturated, saturated, and supersaturated. And I'm going to use good old Texas sweet iced tea as my example of all three of these. Okay? So who in here likes to order sweet tea when they go to the restaurant? Out of one person out of all of these? Okay, 2 people like sweet tea. Okay, who wants to be my example? Stephen or Ryan? Okay, Stephen, you're my example. So Stephen goes to the restaurant and he says, I would like some sweet iced tea. And the waitress says, I'm sorry, hon, we don't have sweet iced tea. We just have unsweet iced tea. So he's like, fine, bring me some unsweet iced tea. So he proceeds to take some sugar, right? And at this point, that solution is unsaturated because I could dissolve some sugar in there, right? So it's unsaturated because I could dissolve some. So he dumps his sugar in there and he stirs, and it's still not very sweet. So he dumps some more, and he stirs and he stirs and he stirs, and he stops stirring, and now he's got a layer of sugar in the bottom, right? And that's because now at that point, when there's a sugar, there's some, we know some did dissolve, but there's some that's not dissolving anymore. So that is now a saturated solution. It has dissolved all that it can, all right, at that temperature. Because solubility is very much dependent upon temperature, okay? So his tea's not very sweet, though, is it? Because at that cold temperature, the saturation point of sugar is very, very low, so it doesn't taste very sweet. However, he goes home and he tells, who makes the sweet tea at your house, Mom or Dad?
Me.
Oh, okay. So tell us how you make sweet tea, Stephen.
I boil water.
You boil water.
And I put the tea packet in.
Uh-huh.
Let the convection of the water
Right.
distribute.
How do you get it sweet? When do you add the sugar? That's what I'm getting at.
Sugar, and I take 3 pitchers because me and my dad drink a lot.
Okay.
I take the pitchers, I pour the sugar in the pitchers.
Uh-huh.
When the tea is done brewing,
Uh-huh.
I'll pour tea in each one.
While the water is
Hot.
hot. Yeah, that's what I'm trying to get at. So you put the sugar in there while the water is hot, get it to dissolve, and then you cool it back down. You probably drink it with ice, same temperature as the restaurant, right? But now, because you heated it up, added more sugar at a higher temperature, and cooled it back down, now you have a supersaturated solution. Because at that temperature, you have more than you should. So that's what a supersaturated solution is. By the way, you might want to put a little star by supersaturated. They are very unstable, okay? Because they have more than they should. And so oftentimes it just takes a little seed crystal or something to agitate it or disturb it, and it'll start crystallizing out. If you leave that sweet tea, let's say you made a pitcher and you went on vacation, you got to go to, I don't know, Iceland for 10 days. Shameless plug. And you come back and you take out your iced tea pitcher and it has no one's bothered it and it's been sitting there. Sometimes there's often like a big solid thing of sugar at the bottom, and it's because you were unsaturated and it crystallized out. It's exactly how they make rock candy, by the way. Okay, if you want to make rock candy, you can go home and make some in the next couple of days. Take a cup of water, dissolve about 2.5 to 3 cups of sugar, maybe even put a little flavored extract in there. Maybe you want root beer flavored rock candy, I don't know. And then put it in a glass, put a string or a stick with some sugar coating on it and let it sit, and you'll get rock candy. It's pretty easy. It won't be as pretty as what you buy in the store because they're doing that professionally, but that's how you make rock candy. You make a supersaturated solution and it crystallizes out. Okay? So that's going to take us to our solubility curve. Yes, Ray?
Is this where we get saturated and unsaturated fats?
No, that has to do with their bonds, whether they have double bonds or single bonds in their carbon chain. Yeah, that's totally different. But that's a good question because that's probably where you've heard those terms before. You know, yeah. Like polyunsaturated fats and all that stuff. That has to do with the bonds. That's an organic thing, organic chemistry. Yeah. Okay, so this is a solubility curve. Notice that it's 100 grams for your solvent of water. If I have 100 grams of water, how many milliliters of water do I have? 100. Very good, because the density of water is 1 gram per milliliter. Okay, so if you notice, generally the solids or the ionic compounds, generally they increase with increasing temperature, their solubility. The NH3, what does it do? It goes way down. That's because that NH3 is a gas that has different solubility issues with temperature. So the way that I would read this, we're going to use KNO3 as an example. And if I were to read this, and we're going to use 50 degrees. So all of my questions are going to be about 50 degrees Celsius, and all of my questions here are going to be about KNO3 in the notes, not the worksheet. Okay? So if I look at it and I say at 50 degrees Celsius, how much KNO3 can I dissolve in water? 80, right? Right? 80, okay? So if I tell you at 50 degrees Celsius, I have 80 grams of KNO3 dissolved in my water, that means I have what kind of solution if I'm right on the line?
Saturated.
Saturated. I have the maximum amount, okay? What if I said, okay, at 50 degrees, I have 40 grams? Then I would be unsaturated, right? But let's say I heated it up and I dissolved 120, and then I cooled it back down to 50 degrees. So I'm at 50 degrees and I have 120 grams dissolved. What kind of solution do I have? Supersaturated. So that's how you read that chart, okay? What if I said, how many grams could I dissolve, how many grams of KNO3 could I dissolve in 200 grams of water at 50 degrees Celsius? 160, right. I would just double it, right? If I can do 80 and 100 grams, I can do 160 and 200 grams. That makes sense, right? So that's how you read this chart, and that's how you'll use this chart on your homework, okay? Now, we're almost done. Got a couple more definitions. We do the math tomorrow. We do the definitions today. Factors affecting the rate of solubility. Rate of solubility. So these three things are not how much, this is how fast can I make it dissolve. And all of that, all of those words, which is a lot of words, explaining it more extensively, can all be broken down into heat it, crush it, stir it. So we're going to go back to our iced tea example, right? We want to make sweet iced tea. So Stephen, when you dump that sugar into your tea, do you just dump it in there and let it sit, or what do? You stir it. Why does he stir it? Why does it make it mix up faster? I'm going to tell you why. I'm glad you asked. Okay, so I put my sugar in there, and let's say I don't stir it. Okay, so the sugar obviously sinks to the bottom, and then what happens is the sugar's down at the bottom, right? The only thing that's interacting is that water layer that's right there with the sugar. So if it's the only thing reacting, what do you think? Not reacting, that's the wrong word, because they're not. Interacting is the word. So the only thing interacting is that layer of water right above the sugar. Well, what do you think happens to that layer of water right above the sugar? It gets, well, what's another word that we're using for filled up? Saturated. That layer gets saturated. So the purpose of stirring it is it's introducing fresh solvent to the solute. So now it dissolves faster. Okay. And then when you're making your sweet tea, Stephen, do you use crystallized sugar or do you use sugar cubes? Do you even have sugar cubes? Yeah. Why would you not want to use sugar cubes versus sugar crystals?
It's only interacting with
Exactly. If you have sugar cubes, it's only interacting with the outside of that sugar cube, right? It's got to dissolve it layer by layer by layer. So it has a smaller surface area than the ones that have all been crushed up, right? So that's why we want to use crystallized sugar and not sugar cubes. Although if you go to a fancy restaurant, they like to give you the sugar cubes because it's cute and fancy and all that stuff. Okay, but it dissolves slower. Okay, and then the last thing, of course, is he said the first thing he does is do what to the water? Boil it, because the solubility, not only is it, even if it doesn't increase the solubility, it will dissolve faster. Okay, so it'll be much faster. Because what's happening when the particles, when they're heated up, what are they doing? They're heat them up, speed them up, right? So the particles are moving faster, so now that's more interactions with the solute and the solvent. So that's why heat it, crush it, stir it makes things dissolve quicker, more quickly. Quicker's not a word, is it? Quickly or? I don't teach English. Faster, we'll go faster, yeah. Because I know more fast is not right. Is it more quick or quicker?
I think it's quicker.
Quickly, yeah, quick. Anyway, heat it, crush it, stir it. So if they're asking you a question on the test about that, think to yourself, heat it, crush it, stir it. Okay, now factors that will affect the solubility. So now we're not talking about rate, we're talking about how much, okay? And so first thing we're going to talk about is increasing temperature. And it says generally, when I increase the temperature, I generally will increase the amount of solid that will dissolve in a liquid. There are some exceptions, but generally it does. So if I ask you if it always increases it, would the answer be no? Generally, meaning there's some exceptions, okay?
Wouldn't NH3 be an exception?
NH3 is not a solid. But I'm glad you asked that. Because decreasing the temperature increases the solubility of a gas in a liquid. So that's why in our solubility curve we see NH3 plummet as we heat it up. Because NH3 is a gas, and so the solubility will, it's actually a direct relationship. Like if I increase the temperature, my solubility goes down. Okay? So I'm going to take you back to now not drinking tea anymore. We're going to drink soda or a sody water if you're up north, or pop. Or as we call them in Texas, we're drinking a Coke. We might be drinking a Dr. Pepper, but we're drinking a Coke, right? And so would you rather drink a hot room temperature Coke or a cold Coke? Why? What happens when it's warm? It goes flat really fast, right? Yeah, because the solubility of the CO2 in a warm liquid is not as much, okay? So if you have, you got a Coke or a pop, whatever you want to call it, and you have its room temperature, and you pour that over ice, it goes flat really fast, right? Much faster than if it's cold poured over ice. And that's because of that temperature difference. When it gets fizzy, all bubbly up really quick, we call that effervescence. It's basically the rapid release of a gas. Our last lab we did for stoichiometry, where we did the baking soda and the vinegar, or I gave you the real names, sodium bicarbonate and acetic acid, and it bubbled up real quick. That's effervescence. That's a rapid release of a gas. Okay? And then the last thing that affects it is pressure, and it is a direct relationship. So let's go open our Coke. What sound does it make? Psh. And what that is, it's releasing the pressure. All soda has a layer of gas on top, and they put a pressure on it, and that is what is forcing that CO2 to stay in your carbonated beverage, which is why once you open it, even if you put it back in the refrigerator, once it's been opened, it's going to eventually go flat because you've released that layer of pressure. Keeping it in the refrigerator helps it go flat more slowly, but that's why. Well, yeah, put the cap back on it too, because then you kind of like, what gas is being released, it kind of keeps the pressure in the cap. Okay? So those are the things that affect the solubility. Pressure only matters for gases in a liquid. So make sure you underline that. The words I wrote in red, y'all should have probably underlined those, by the way, because that's the important part of that.
It's a little late.
That's a little late, yeah. I mean, I would think that, how many of you underlined the words in red because I was emphasizing them? One person, Maddie. See, now you doubly deserve that brownie. All right, when we're talking about solutions, we're going to refer to them as concentrated or dilute, okay? Concentrated means there's a whole lot of solute in relationship to the solvent, and then dilute means there's not very much. Best example of a concentrated solution is Tide Pods, right? Because there's a whole lot of solute in that little portion, okay? And then a dilute solution is once I've added water to it. Y'all don't really see this much anymore. We were, when I was a kid, people used to buy orange juice concentrate. Has anybody ever seen orange juice concentrate? Yeah, it's like comes in a can, right? You would never want to drink or eat that because it's like syrupy and thick. But what you do is you take that orange juice concentrate, you put it in your pitcher, and then usually I think it says add 3 cans of water, and then you dilute that concentrate, stir it up, and now you have it's called reconstituted orange juice. It's supposed to taste like the real thing, but it doesn't. Okay, but that would be an example of diluting it. Okay. Kind of like, well, powdered milk would be making a solution because it's not. We wouldn't call that concentrated. Yeah. Okay. And then lastly, we have electrolytes, and then we're done for the day. I know it's kind of a long lesson, but it's got to get all this other stuff out of the way. Okay. Electrolytes, of course, are things that will conduct electric current when they're aqueous or in their molten state. You can have a strong, a weak, and a non-electrolyte. You do need to know all of that. All those words you need to know. You need to know the strong acids, because they are strong electrolytes, ionic compounds, and then weak acids and weak bases are your weak electrolytes. Meaning a little bit dissolves, they'll conduct a small current, but they're not real strong at it. Okay? And now we're done with all the housekeeping, definitions, and review. Tomorrow we'll do the math.